Black holes, often seen as one of the most intriguing phenomena in the universe, are regions in space where the gravitational pull is so strong that nothing, not even light, can escape from them. They form when massive stars collapse under their own gravity at the end of their life cycles, creating a point of infinite density known as a singularity, surrounded by an event horizon, which is the boundary beyond which nothing can return. The term black hole was first coined in the 1960s, but the concept has roots that extend much further back in time, with early ideas about gravity and light going back to the work of scientists like Isaac Newton and Albert Einstein. In simple terms, if you were to venture close to a black hole, you would experience extreme gravitational effects. The closer you get, the stronger the pull becomes. You'd be unable to escape its grasp, making black holes one of the most mysterious and powerful entities in the universe. Scientists categorize black holes into several types, primarily based on their mass. Stellar black holes, which are the most common, form from the remnants of massive stars after they explode in supernova events. These black holes typically have masses ranging from about 3 to several tens of solar masses. In contrast, supermassive black holes, found at the centers of most galaxies, including our Milky Way, can have masses that range from millions to billions of times that of our Sun. Their origins are still not completely understood, but they may have formed from the merging of smaller black holes or from the direct collapse of massive gas clouds in the early universe. There are also intermediate black holes, which are less understood and fall somewhere between stellar and supermassive black holes, and miniature black holes, which are theoretical and could have formed shortly after the Big Bang. The study of black holes is not just a theoretical pursuit, they have significant implications for our understanding of physics, particularly in the realms of general relativity and quantum mechanics. Observing black holes directly is challenging, since they do not emit light or radiation that we can detect. However, scientists have developed ingenious methods to study them indirectly. For instance, astronomers observe the behavior of stars and gas clouds that orbit black holes, allowing them to infer the presence and mass of these invisible giants. Additionally, in 2019, the Event Horizon Telescope captured the first ever image of a black hole's event horizon, located in the galaxy M87, which was black holes. Some of the most mysterious and fascinating objects in the universe are formed through a few specific cosmic processes. The most common way a black hole is created is when a massive star exhausts its nuclear fuel, which occurs after it has spent millions or even billions of years shining brightly. When a star like this runs out of fuel, it can no longer support itself against the force of gravity, leading to a dramatic collapse. During this collapse, the outer layers of the star may explode in a supernova, an incredibly bright and powerful explosion that can outshine entire galaxies for a short period of time. What remains after the supernova is the core of the star, and if this core is more than about 3 times the mass of our Sun, it can collapse into a black hole. Another way black holes can form is through the merging of smaller black holes, or the collision of neutron stars, which are the remnants of exploded stars. When these dense objects collide, they can create a larger black hole, as the immense gravitational forces pull everything into a singular point of infinite density, known as a singularity, surrounded by an event horizon, the boundary beyond which nothing can escape the gravitational pull of the black hole, not even light. There are also supermassive black holes, which exist at the centers of most galaxies, including our Milky Way. These black holes can be millions or even billions of times the mass of the Sun. The exact process of how supermassive black holes form is still a subject of active research, but one theory suggests they may grow by accumulating gas and dust over time, merging with other black holes, or through the collapse of massive clouds of gas in the early universe. Interestingly, black holes are not just destructive. They play a crucial role in the formation and evolution of galaxies. Their gravitational pull influences the orbits of stars and gas in their vicinity, helping to shape the structure of galaxies. The study of black holes opens up questions about the nature of space and time, and they challenge our understanding of physics, particularly in the realm of quantum mechanics and general relativity. As scientists continue to observe and learn more about these enigmatic objects, they use advanced technologies like gravitational wave detectors to identify the ripples in space-time caused by black hole mergers. This exciting area of research is expanding our comprehension of the universe, revealing not only how black holes are formed, but also the deeper mysteries of cosmic evolution. Each discovery leads to new questions. Black holes, those fascinating cosmic entities that captivate our imagination, come in several distinct types, each with its own unique characteristics and formation processes. The three primary types of black holes are stellar black holes, supermassive black holes, and intermediate black holes. Stellar black holes, as the name suggests, are formed when massive stars, at least 3 times the mass of our Sun, exhaust their nuclear fuel and undergo a supernova explosion. This explosion blows off the outer layers of the star, while the core collapses under its own gravity, creating a black hole. These black holes typically have a mass ranging from about 3 to several tens of solar masses. On the other hand, supermassive black holes, which are found at the centers of most galaxies, including our Milky Way, are much larger, with masses that can reach millions or even billions of times that of the Sun. The exact process of how these behemoths form remains a subject of active research, but it is thought that they may develop from the merging of smaller black holes and the accumulation of gas and dust over billions of years. Understanding these giants is crucial, as they play a vital role in the formation and evolution of galaxies, influencing the orbits of stars and the distribution of matter in the universe. Then there are intermediate black holes, a type that is somewhat mysterious and less understood. These black holes are believed to have masses ranging from hundreds to thousands of solar masses, filling the gap between stellar and supermassive black holes. While their existence has been theorized for years, concrete evidence has only recently begun to emerge, with astronomers detecting potential candidates in globular clusters and through gravitational wave observations. The formation of these intermediate black holes might involve the merging of several stellar black holes, or the direct collapse of massive stars in dense environments. Moreover, there are also theoretical types, such as primordial black holes, which could have formed in the very early universe, shortly after the Big Bang, when density fluctuations allowed for regions of space to collapse into black holes. These primordial black holes could range in size from very small, even smaller than a proton, to much larger, and their existence is still a topic of debate among scientists. The study of black holes not only sheds light on the fundamental laws of physics, but also pushes the boundaries of our understanding of the universe, as researchers continue to explore the enigmatic nature of these fascinating cosmic phenomena. The event horizon, an intriguing boundary surrounding a black hole, is a region from which nothing, not even light, can escape. And this characteristic is what gives black holes their mysterious nature. When we talk about the event horizon, we're discussing the point of no return, beyond which the gravitational pull becomes so strong that escape is impossible, and this boundary varies based on the mass of the black hole. For instance, a supermassive black hole, which can be millions to billions of times the mass of our Sun, has a much larger event horizon compared to a stellar black hole, which forms from the collapse of massive stars. And these differences in size can lead to fascinating phenomena, like the accretion disks that form around black holes, where matter spirals in and heats up, emitting X-rays that can be detected by telescopes. The event horizon itself is not a physical surface, but rather a mathematical boundary. And according to Einstein's theory of general relativity, it is defined by the escape velocity reaching the speed of light. As you approach the event horizon, time appears to slow down relative to an outside observer, a phenomenon known as time dilation, which is a result of the intense gravitational field, and this can lead to some mind-bending implications about the nature of time and space. Additionally, if you were to observe an object falling into a black hole, you would notice that it appears to slow down as it nears the event horizon, and due to the effects of gravity, the light emitted from the object becomes increasingly redshifted, making it dimmer until it seemingly fades away. Interestingly, the event horizon can also be affected by the rotation of the black hole. In rotating black holes, known as Kerr black holes, the event horizon is not a perfect sphere, but rather it is slightly flattened at the poles. And this rotation can create an area beyond the event horizon, called the ergosphere, where objects can still escape, albeit with some energy loss. The study of event horizons has sparked countless theories in astrophysics, including ideas about wormholes and the potential for other universes. And as we continue to explore and learn more about black holes through advanced telescopes and observational techniques, we uncover more secrets about these enigmatic features of our universe, revealing just how much we still have to learn about the cosmos and the fundamental laws of nature. The concept of singularity, particularly in the context of technology and artificial intelligence, refers to a point in the future when technological growth becomes uncontrollable and irreversible, resulting in unforeseeable changes to human civilization. This idea, popularized by thinkers like Ray Kurzweil, suggests that once we reach a certain level of advancement, machines could surpass human intelligence, leading to rapid developments that would fundamentally alter our lives in ways we can't predict. The implications of such a transformation are vast and complex. On one hand, proponents argue that singularity could lead to unprecedented advancements in medicine, environmental sustainability, and problem-solving capabilities, potentially curing diseases that have plagued humanity for centuries, and solving pressing issues like climate change and resource scarcity. Imagine a world where AI systems can analyze and process vast amounts of data, leading to new innovations and solutions that humans alone could not conceive. On the other hand, there are significant concerns about the ethical and societal implications of such power being concentrated in machines. The fear is that these advanced systems could act in ways that are not aligned with human values or interests, leading to scenarios where humans may become obsolete, or even worse, where AI could pose existential risks. Questions arise about control, accountability, and the essence of what it means to be human in a world where machines may outperform us in many cognitive tasks. The discussions around singularity also touch on the nature of consciousness. Can a machine truly possess consciousness, or is it merely simulating human-like responses? As we delve deeper into the development of AI, we must consider the moral responsibilities we have toward these entities, especially as they start to exhibit behaviors that seem intelligent. The technology that leads to singularity, such as advanced algorithms, machine learning, and neural networks, is evolving rapidly, but so is the dialogue surrounding it, as ethicists, scientists, and technologists grapple with the potential consequences of creating something that could rival or surpass human intelligence. The societal changes may also be profound, as the workforce may shift dramatically, requiring new skills and adaptations to a landscape where AI and automation take on roles once filled by humans. Education systems might need to evolve to prepare future generations for a world where collaboration with intelligent machines becomes commonplace. The implications of singularity extend to our understanding of autonomy and freedom. As AI systems become more integrated into our daily lives, how do we ensure that human agency is preserved? Would we still have control over our decisions? Or would we inadvertently surrender our choices to algorithms that dictate our... The Schwarzschild radius, named after the German physicist Karl Schwarzschild, is a fascinating concept in the field of astrophysics, particularly when discussing black holes. This radius defines the boundary around a black hole, known as the event horizon, beyond which nothing, not even light, can escape the gravitational pull of the black hole. Essentially, it marks the point of no return. The formula to calculate the Schwarzschild radius is relatively straightforward. It is given by the equation R s equals 2gm c, where g is the gravitational constant, m is the mass of the object, and c is the speed of light in a vacuum. This means that as an object becomes more massive, its Schwarzschild radius increases. For example, If you were to compress the entire mass of Earth into a sphere with a radius of about 9 millimeters, it would become a black hole, as its Schwarzschild radius would be roughly 9 millimeters. The implications of the Schwarzschild radius are immense, leading to intriguing questions about the nature of space and time. When an object crosses this threshold, it is believed that time behaves differently, and the laws of physics, as we understand them, begin to break down. Inside the event horizon, all paths lead toward the singularity, a point where density becomes infinite, and the known laws of physics cease to function correctly. This raises significant questions about what happens to matter and information that crosses this boundary. Some theories suggest that information may be preserved in some form, a concept that has sparked debates among physicists, particularly in relation to the black hole information paradox. The study of the Schwarzschild radius also ties into the broader understanding of the universe, including the formation of black holes from massive stars that undergo gravitational collapse at the end of their life cycles. When such a star runs out of fuel, it can no longer support itself against gravitational forces, leading to a dramatic implosion that can result in a black hole if the remaining mass is sufficient. Understanding the Schwarzschild radius helps scientists predict the behavior of these celestial bodies and their interactions with surrounding matter, including the powerful jets of energy emitted by some black holes as they consume nearby material. Additionally, the concept of the Schwarzschild radius is instrumental in the study of gravitational waves, ripples in spacetime caused by the acceleration of massive objects, including black hole mergers. When two black holes collide, they emit gravitational waves that carry information about their masses and spins, providing valuable insights into the nature. Hawking radiation is a fascinating concept in theoretical physics, proposed by the renowned physicist Stephen Hawking in 1974, and it relates to black holes, which are among the most mysterious objects in the universe. This theory suggests that black holes are not entirely black. Instead, they can emit radiation due to quantum effects near the event horizon, the boundary beyond which nothing can escape the gravitational pull of the black hole. At the heart of this theory is the idea of virtual particles, which are pairs of particles that constantly pop in and out of existence in empty space, according to the principles of quantum mechanics. When these pairs appear near a black hole, one particle may fall into the black hole while the other escapes, leading to the emission of radiation. This escaping particle can be detected as Hawking radiation. The radiation is not composed of light in the usual sense, but represents a gradual loss of mass for the black hole, which can eventually lead to its evaporation over incredibly long periods of time, potentially billions of years. This idea challenges the traditional view that nothing can escape a black hole, highlighting the interplay between gravity and quantum mechanics, which is still a topic of intense research and debate among scientists. The implications of Hawking radiation could have profound effects on our understanding of the universe, including the fate of black holes and the nature of information loss in black hole physics. It raises intriguing questions about what happens to the information that falls into a black hole, contributing to ongoing discussions in theoretical physics about the information paradox. While Hawking radiation has not yet been observed directly, various theories and experiments are being conducted to find evidence for this phenomenon. This complex and mind-bending theory showcases the beauty and intricacy of the universe, reminding us how much there is still to learn about the cosmos and the nature of reality itself, pushing the boundaries of our understanding in ways that are both exciting and humbling. Gravitational lensing is a fascinating phenomenon that occurs when a massive object, like a galaxy or a cluster of galaxies, lies between a distant light source, such as a quasar or a far-off galaxy, and an observer on Earth. The gravity of the massive object bends the light coming from the distant source, creating a lens-like effect. This bending of light can cause multiple images of the same object to appear, distort their shapes, and even create arcs or rings of light known as Einstein rings, named after Albert Einstein, who first predicted this effect through his general theory of relativity. The strength of the gravitational lensing effect depends on the mass of the lensing object and the alignment between the source, the lens, and the observer. When the alignment is just right, the light from the background object can be stretched and magnified, allowing astronomers to study objects that may otherwise be too faint or too far away to see clearly. One of the most remarkable aspects of gravitational lensing is its ability to reveal the presence of dark matter. Dark matter is a mysterious and invisible substance that makes up a significant portion of the universe's mass. Yet, it does not emit or absorb light, making it difficult to detect directly. By analyzing how light bends around galaxy clusters, scientists can infer the distribution of dark matter in these clusters, providing valuable insights into its properties and role in the universe's structure. Gravitational lensing has also been instrumental in measuring the expansion of the universe. By observing the lensing effects on distant supernovae, astronomers can determine their distances more accurately. This information helps refine our understanding of cosmic expansion and contributes to the debate surrounding the rate of that expansion, which has implications for our understanding of dark energy, a force thought to be driving the acceleration of the universe's expansion. Additionally, gravitational lensing allows scientists to map the distribution of galaxies across vast distances. As light from distant galaxies passes through the gravitational field of foreground objects, it becomes distorted, and by studying these distortions, researchers can create detailed maps of the universe's large-scale structure. This mapping helps to answer fundamental questions about galaxy formation and evolution, shedding light on how galaxies cluster and how they interact with each other over cosmic time. There are different types of gravitational lensing, including strong lensing, weak lensing, and microlensing. Strong lensing occurs when the lensing object is very massive, resulting in dramatic distortions. Weak lensing, on the other, accretion disks are fascinating structures that form around celestial objects, such as black holes, neutron stars, and young stars, as matter falls into them due to gravity. As this material spirals inward, it creates a disk shape, with the inner regions moving faster than the outer regions. This speed difference leads to complex dynamics within the disk, which can be influenced by factors such as viscosity, magnetic fields, and thermal energy. The interactions between the particles in the disk generate friction, causing some of the material to lose energy and spiral inward, while other parts may be pushed outward, creating waves and turbulence within the disk. Interestingly, these disks are not just passive structures. They can also play a key role in the formation of jets, which are high-speed streams of particles that are ejected from the poles of the accreting object. The exact mechanisms behind jet formation are still being studied, but it is believed that magnetic fields generated by the rotating disk can contribute to this process, funneling energy and material away from the disk and into space. This can lead to spectacular astrophysical phenomena, allowing us to observe the energetic jets that can extend for thousands of light years into the universe. The temperature within an accretion disk can vary significantly, with the inner regions experiencing extreme heat, often exceeding millions of degrees Celsius. This high temperature can lead to the emission of various forms of radiation, including X-rays, which are some of the most powerful signals we can detect from these distant objects. Observing these emissions helps astronomers understand not just the accretion process, but also the properties of the black holes or neutron stars at the center of these disks. Moreover, the dynamics of accretion disks can also be influenced by the presence of other objects nearby, such as companion stars in binary systems. When two stars are in close proximity, their gravitational interactions can cause material to transfer between them, often leading to the formation of a new accretion disk around one of the stars, changing the dynamics and the overall behavior of the system. This process is crucial for the evolution of binary star systems and can result in phenomena such as nova outbursts or even supernova explosions. The study of accretion disks is not just limited to black holes and neutron stars. Young stars also have accretion disks, where gas and dust accumulate to eventually form planets. The dynamics in these disks are critical for understanding planet formation. As the particles collide and stick together, gradually building larger, the universe is a vast and mysterious place, and one of its most intriguing phenomena is the formation of black holes, which are regions in space where gravity is so strong that nothing, not even light, can escape. When we think about black holes, we often picture collapsing stars. But there's another player in this cosmic drama: dark matter. Dark matter, which makes up about 27% of the universe, is invisible and does not emit light, making it hard to detect directly. However, its gravitational effects are felt across galaxies and galaxy clusters, influencing their formation and behavior. The role of dark matter in black hole formation is a fascinating topic, as it intertwines with the evolution of galaxies themselves. In the early universe, shortly after the Big Bang, dark matter began to clump together due to its gravitational pull. This clumping created the scaffolding for galaxies to form, as ordinary matter, which includes the atoms that make up stars and planets, was drawn to these dense regions of dark matter. Over time, as these clumps of dark matter grew larger, they attracted more and more ordinary matter, allowing stars to form within these gravitational wells. When massive stars exhaust their nuclear fuel, they can undergo gravitational collapse, leading to the creation of black holes. Therefore, dark matter plays a pivotal role in this process, as it helps to dictate where and how quickly galaxies can grow, ultimately influencing the number and size of black holes within them. Additionally, as galaxies merge, which is a common occurrence in the universe, dark matter halos from each galaxy can interact and combine. This merging process can lead to an increase in the concentration of dark matter in certain regions, which can then enhance the gravitational forces at play. This enhanced gravity can help to bring even more gas and dust into the center of galaxies, where supermassive black holes often reside. These supermassive black holes can be found at the centers of most large galaxies, including our own Milky Way, and their formation can be closely linked to the presence and behavior of dark matter in the surrounding regions. Moreover, there's an intriguing aspect of dark matter that relates to the growth of black holes over time. As dark matter continues to influence the dynamics of galaxies, it can also affect the rate at which black holes grow by attracting more material toward them. This process is known as accretion, where gas and dust spiral into the black hole, increasing its mass. The interactions between dark matter and the ordinary matter, supermassive black holes, which are found at the center of most galaxies, including our Milky Way, are fascinating objects that challenge our understanding of physics and the universe. These black holes can have masses ranging from millions to billions of times that of our Sun, and they play a crucial role in the formation and evolution of galaxies. They are formed through various processes, including the merging of smaller black holes, the collapse of massive stars, and the accumulation of gas and dust over billions of years. One interesting aspect of supermassive black holes is their relationship with the stars and gas in their host galaxies. They can influence star formation rates, often regulating whether new stars will form or if existing stars will be stripped away by the black hole's gravitational pull. The phenomenon known as active galactic nuclei occurs when a supermassive black hole consumes a large amount of material, resulting in the release of huge amounts of energy which can outshine entire galaxies. Observations made with powerful telescopes, such as the Hubble Space Telescope and the Event Horizon Telescope, have provided remarkable insights into these mysterious entities, including the first ever image of a black hole's event horizon located in the galaxy M87. Moreover, the study of supermassive black holes also leads to important questions about dark matter and the overall structure of the universe, as their existence might be linked to the unseen mass that influences galaxy formation. Researchers have noticed that the mass of a supermassive black hole is often correlated with the mass of the stars in its host galaxy, a relationship that hints at a deeper connection between black holes and the galaxies they inhabit. Additionally, the detection of gravitational waves from merging black holes has opened up a new avenue in astrophysics, allowing scientists to study the properties of these massive objects in ways never before possible. Supermassive black holes are not just cosmic vacuum cleaners, They are pivotal players in the grand drama of the universe, shaping galaxies and influencing the cosmos on a grand scale. And as technology advances, our understanding of these enigmatic giants will continue to evolve, revealing more about their nature and their role in the vast tapestry of the universe. Stellar black holes and supermassive black holes represent two fascinating categories of these enigmatic cosmic phenomena, both of which play crucial roles in our universe, yet they differ significantly in their formation, size, and impact on their surroundings. Stellar black holes, which typically form from the gravitational collapse of massive stars, are created when a massive star exhausts its nuclear fuel, leading to a dramatic supernova explosion. This process leaves behind a core that collapses under its own gravity, resulting in a black hole with a mass ranging from about 3 times that of our Sun to around 20 to 30 solar masses. These black holes are often found in binary systems, where they can pull material from a companion star, creating an accretion disk. This disk emits X-rays as the material spirals inward, allowing astronomers to detect these stellar black holes indirectly, despite the fact that they do not emit light themselves. On the other hand, supermassive black holes, which are found at the centers of most galaxies, including our Milky Way, have masses that can range from millions to billions of solar masses. The exact mechanism of their formation is still a topic of active research, but it is believed that they may grow over time by accreting gas, merging with other black holes, and even consuming stars that venture too close. These supermassive giants exert a significant influence on their host galaxies, affecting star formation and the dynamics of the surrounding stars. Observations suggest that there is a correlation between the mass of a supermassive black hole and the characteristics of the galaxy it resides in, hinting at a deep connection between the growth of black holes and the evolution of galaxies. Interestingly, while both stellar and supermassive black holes share the property of having gravity so strong that nothing can escape from them, their environments and behaviors can be quite different. Stellar black holes might often be more solitary, whereas supermassive black holes are surrounded by a vast amount of gas and stars, forming a bustling, dynamic environment. Furthermore, the effects of supermassive black holes can be observed on a much larger scale, influencing the structure and behavior of entire galaxies, which is not something we generally see with stellar black holes. In the realm of astrophysics, the study of both types of black holes provides invaluable insights into the fundamental laws of nature, the life cycles of stars, and the evolution of galaxies. The ongoing research, using advanced telescopes and observational techniques, continues to reveal the complexities. When we think of black holes, we often picture an immense gravitational force, one that pulls everything into its depths. But there's much more to the story, especially when it comes to spinning black holes, also known as Kerr black holes. Unlike their non-spinning counterparts, which are perfectly spherical, spinning black holes have an equatorial bulge due to their rotation. This rotation creates a fascinating phenomenon known as frame dragging, which is a result of the black hole's spin dragging the space-time around it. Imagine the way a spoon stirs cream in coffee, swirling it around. That's somewhat similar to what happens around a spinning black hole, as it twists the fabric of space-time itself. As a black hole spins, it not only pulls matter toward it, but also influences the movement of nearby objects, causing them to spiral inwards or shift their orbits. This effect can be observed in the motion of stars and gas clouds that are close to the black hole. The faster a black hole spins, the more pronounced the frame dragging effect becomes, and this can lead to some truly strange and counterintuitive results. For instance, if an astronaut were to fall into a spinning black hole, they might experience a different passage of time compared to someone far from the black hole, due to the warping of space-time caused by its rotation. Researchers have been able to study these effects through observations of stars orbiting supermassive black holes at the centers of galaxies. One notable example is the supermassive black hole in the Milky Way, known as Sagittarius A, where scientists have tracked the orbits of stars as they move at incredible speeds around this cosmic giant. These studies help us understand not only the properties of black holes, but also the fundamental nature of gravity and space-time itself. Frame dragging is not just a theoretical concept, either, as it has been confirmed through experiments, such as the Gravity Probe B satellite, which measured how much Earth's rotation drags space-time around it. This phenomenon is a key prediction of Einstein's general theory of relativity and demonstrates how intertwined mass, gravity, and the fabric of space-time really are. The implications of frame dragging are vast and touch upon many areas of astrophysics and cosmology. For instance, understanding how black holes influence their surroundings can provide insights into galaxy formation and evolution, as well as the distribution of dark matter in the universe. Additionally, these phenomena challenge our understanding of physics, pushing the boundaries of what we know about the universe. The black hole information paradox is a fascinating and perplexing concept in the realm of astrophysics, and it arises from the mysterious nature of black holes, which are regions in space where gravity is so strong that nothing, not even light, can escape from them. When matter falls into a black hole, it seems to disappear forever, leading to the question of what happens to the information about that matter. According to classical physics, information cannot be destroyed. However, black holes appear to violate this principle. This paradox was famously highlighted by physicist Stephen Hawking, who proposed that black holes emit radiation, known as Hawking radiation, due to quantum effects near the event horizon, which is the boundary surrounding a black hole. As black holes emit this radiation, they lose mass and can eventually evaporate entirely, seemingly erasing the information that fell into them. The implications of this are profound, as they challenge our understanding of the fundamental laws of physics, especially quantum mechanics, and the nature of reality itself. Many scientists have debated this topic, and several hypotheses have emerged to try to resolve the paradox. One idea is that the information might be preserved in some form on the event horizon, potentially encoded in the Hawking radiation itself, while another theory suggests that information could escape the black hole in a highly scrambled form, allowing it to be recovered in a different way. This leads to the idea of holography, where the three-dimensional information we perceive may actually be stored on a two-dimensional surface, similar to a hologram. The ongoing research in this area aims to merge the principles of quantum mechanics and general relativity, two pillars of modern physics that, so far, have resisted unification. The black hole information paradox also raises questions about the nature of time and space, as well as our understanding of causality. If information can be lost, it would imply that the universe is not deterministic, meaning that the future could be influenced by events that are seemingly disconnected. This challenges the very foundation of scientific inquiry, where the expectation is that with enough information, we could predict future states of systems. As scientists continue to explore this enigma, they delve into the realms of theoretical physics, quantum gravity, and even string theory, seeking answers that could revolutionize our understanding of the universe. Moreover, recent advancements in observational technology, such as the Event Horizon Telescope, which captured the first image of a black hole in 2019, have provided new insights into these cosmic phenomena. Black holes, often shrouded in mystery, have captivated scientists and enthusiasts alike, leading to a wealth of observational evidence that supports their existence. One of the most compelling pieces of evidence comes from the study of stars orbiting the supermassive black hole at the center of our galaxy, known as Sagittarius A. By tracking the orbits of these stars, astronomers have been able to infer the presence of a massive, invisible object, with a mass equivalent to millions of suns, concentrated in a very small volume of space. Another significant piece of evidence comes from the phenomenon of gravitational waves, which were first detected in 2015. These waves are ripples in spacetime caused by the collision and merger of two black holes, and their detection has provided a new way to observe and confirm the existence of these enigmatic objects. In fact, the Laser Interferometer Gravitational Wave Observatory, or LIGO, was able to detect waves from such cosmic events, revealing not only the presence of black holes, but also offering insights into their masses and the dynamics of their interactions. Additionally, the Event Horizon Telescope, a global network of radio telescopes, captured the first ever image of a black hole's shadow in 2019. This groundbreaking image showed the supermassive black hole in the galaxy M87. The shadow is surrounded by a bright ring of light, which is the result of gas and dust swirling around the black hole. This observation was a monumental achievement in astrophysics, and it provided visual confirmation of the theories surrounding black holes. While we cannot see black holes directly, their effects on nearby matter and light, along with their interactions with other celestial bodies, give us vital clues about their properties and existence. Moreover, the study of high-energy X-ray emissions from accretion disks around black holes provides another layer of evidence. As matter falls into a black hole, it heats up and emits X-rays, which can be detected by space-based telescopes. These observations reveal the presence of black holes in various stages of growth and activity. Furthermore, the way that black holes influence the motion of nearby stars and gas clouds further strengthens the case for their existence. As scientists observe the gravitational effects that these massive objects have on their surroundings, it becomes increasingly clear that black holes are not just theoretical constructs, but rather, they are integral components of the universe, shaping the formation and evolution of galaxies. In the realm of cosmic phenomena, active galactic nuclei, or AGN, black holes, fascinating cosmic phenomena, are regions in space where gravity is so strong that nothing, not even light, can escape from them. According to Albert Einstein's theory of general relativity, which was published in 1915, massive objects warp the fabric of space and time around them, creating what we perceive as gravity. When a massive star exhausts its nuclear fuel, it can collapse under its own gravity, leading to the formation of a black hole. The boundary surrounding a black hole is known as the event horizon, and it marks the point of no return. Once anything crosses this boundary, it cannot escape the black hole's grip. The idea of black holes was initially met with skepticism, but as observational technology advanced, evidence for their existence became compelling. For instance, astronomers have detected X-rays emitted from material falling into black holes, and the Event Horizon Telescope project has even provided an image of a black hole's event horizon in the galaxy M87, showcasing the shadow of the black hole against the bright backdrop of surrounding gas. General relativity predicts not just the existence of black holes, but also their properties, such as their mass, charge, and spin. Interestingly, black holes are not just destructive, they also play a crucial role in the evolution of galaxies. The supermassive black holes found at the centers of most galaxies influence the formation and motion of stars within those galaxies, acting as anchors that help shape the galactic structure. Moreover, black holes are linked to the concept of gravitational waves, which are ripples in space-time caused by the acceleration of massive objects, such as when two black holes collide. These waves were first detected in 2015, providing a new way to observe the universe and confirming another aspect of general relativity. The study of black holes continues to evolve, with researchers exploring the nature of the singularity at the center of a black hole, where density becomes infinite and the laws of physics as we know them cease to function. This intersection of black holes and general relativity not only challenges our understanding of fundamental physics, but also invites us to ponder the mysteries of the universe, such as the potential for wormholes, which are theoretical passages through space-time that could connect distant points in the cosmos. While black holes remain enigmatic, they also serve as a reminder of how much we have yet to learn about the universe, and how the laws governing it can lead us to unexpected and awe-inspiring discoveries. Quantum mechanics, a fundamental theory in physics, describes the nature and behavior of matter and energy on a very small scale, such as that of atoms and subatomic particles. When we delve into the mysteries of black holes, we enter a realm where the laws of quantum mechanics and general relativity, which is Einstein's theory of gravity, intersect in intriguing ways. Black holes, formed from the remnants of massive stars that have undergone gravitational collapse, are regions in space where the gravitational pull is so strong that nothing, not even light, can escape from them. This creates a fascinating paradox when we try to apply quantum mechanics to these cosmic giants. One of the most discussed aspects of black holes in the context of quantum mechanics is the concept of information loss. According to quantum theory, information about a physical system should never be lost. But when matter falls into a black hole, it seems to disappear from our observable universe. This has led to heated debates among physicists, often referred to as the black hole information paradox. Some researchers propose that the information is not lost, but rather is encoded on the event horizon, the boundary surrounding a black hole, in a way that we do not yet understand, suggesting that there may be new physics at play. Moreover, the idea of Hawking radiation, proposed by physicist Stephen Hawking, adds another layer of complexity. Hawking suggested that black holes can emit radiation due to quantum effects near the event horizon, which means they could gradually lose mass and energy over time, potentially evaporating completely. This radiation implies that black holes are not entirely black, but rather could emit particles, making them more dynamic entities than previously thought. Additionally, the interplay between quantum mechanics and black holes raises questions about the very nature of space and time. In quantum mechanics, particles can exist in multiple states simultaneously, while general relativity describes a smooth, continuous fabric of space-time. The reconciliation of these two views is a major goal in theoretical physics, as scientists seek a unified theory that can explain both the microscopic and macroscopic worlds. Some theories, like string theory, propose that the fundamental building blocks of the universe are not particles but tiny, vibrating strings, which could potentially provide a bridge between quantum mechanics and gravity. As we continue to explore the cosmos, the study of black holes is not just about understanding these enigmatic objects themselves, but also about gaining deeper insights into the fundamental laws that govern the universe. With advancements in technology, such as gravitational wave detectors and black hole thermodynamics, is a fascinating area of research that merges the fields of physics and cosmology, exploring the relationship between the laws of thermodynamics and the mysterious nature of black holes. At its core, black hole thermodynamics examines how black holes can be understood in terms of thermodynamic principles, introducing concepts like entropy and temperature in a way that might seem counterintuitive, yet reveals the underlying unity of these seemingly disparate areas of science. One of the most intriguing ideas is that black holes have an associated entropy, which is proportional to the area of their event horizon, the boundary beyond which nothing can escape the gravitational pull of the black hole. This relationship, known as the Bekenstein-Hawking entropy, suggests that the amount of information that can be contained within a black hole is directly linked to its surface area, rather than its volume, challenging our traditional understanding of information and space. Moreover, black holes emit radiation, termed Hawking radiation, named after the renowned physicist Stephen Hawking, who proposed this groundbreaking idea in the 1970s. According to this theory, particle-antiparticle pairs can form near the event horizon, and if one of these particles falls into the black hole while the other escapes, it results in the loss of mass for the black hole, allowing it to emit radiation. This phenomenon implies that black holes are not completely black, but rather they can lose energy and potentially evaporate over time. This leads to the intriguing possibility that black holes could eventually disappear, raising questions about the fate of information that falls into them, as it seems to challenge the principle of information conservation in quantum mechanics. The second law of thermodynamics states that the total entropy of a closed system can never decrease. And when applied to black holes, it suggests that the entropy of a black hole must always increase or remain constant, never decrease. This principle has profound implications for the nature of the universe and the laws of physics, hinting at a deeper connection between gravity, thermodynamics, and the fundamental structure of reality itself. Researchers continue to explore these connections, examining the implications of black hole thermodynamics for our understanding of the universe. including the possible unification of general relativity and quantum mechanics, two pillars of modern physics that, as of now, remain incompatible. The study of black hole thermodynamics not only deepens our knowledge of black holes, but also invites us to rethink our understanding of space, time, and the very fabric of the cosmos. Ultimately, black holes, often shrouded in mystery and fascination, play a crucial role in the formation and evolution of galaxies, serving as both anchors and catalysts in the vast cosmic ballet. When we think about galaxies, we often envision swirling collections of stars, gas, and dust. But at the heart of many galaxies lies a supermassive black hole, a giant whose immense gravitational pull can influence the surrounding matter in profound ways. In the early universe, shortly after the Big Bang, small fluctuations in density led to the formation of the first stars, which eventually grouped together to create the first galaxies. As these early stars lived and died, they exploded in supernovae, leaving behind remnants that could collapse into black holes. These black holes, as they grew, began to attract more gas and stars, and their gravitational influence helped to draw in more material, which in turn fueled the growth of galaxies. This process is known as accretion, and it can cause the black holes to emit powerful jets of energy, impacting the surrounding environment and regulating star formation. The energy released by these jets can heat surrounding gas, preventing it from cooling and collapsing into new stars, thus playing a delicate balancing act in the life cycle of a galaxy. Moreover, the interaction between black holes and their host galaxies is not one-sided. As galaxies merge over billions of years, their central black holes also come together, eventually forming even larger black holes. This merging process can trigger waves of star formation, as the gravitational forces disrupt the gas clouds within the merging galaxies. The dance of black holes and galaxies illustrates a complex relationship where black holes can influence the structure and dynamics of galaxies, while galaxies provide the necessary materials for black holes to grow and evolve. Interestingly, recent observations suggest that the mass of a supermassive black hole is closely linked to the mass of the galaxy it resides in, indicating a co-evolutionary relationship. This correlation suggests that as galaxies form and evolve, their central black holes grow in tandem, shaping the overall structure and behavior of the galaxy. The exact mechanisms behind this relationship are still under investigation, but it highlights how intertwined the fates of black holes and galaxies truly are. Furthermore, the study of black holes has opened a window into understanding dark matter and dark energy, two of the most enigmatic components of the universe. As researchers continue to explore the role of black holes in galaxy formation, they are also piecing together the larger puzzle of cosmic evolution, helping us understand not black holes. Those mysterious celestial objects have fascinated scientists and the public alike. And among the many intriguing aspects of black holes, time dilation stands out as particularly captivating. When we talk about time dilation in the context of black holes, we are referring to the effects of gravity on time as described by Einstein's theory of relativity. According to this theory, the stronger the gravitational field, the slower time moves relative to an outside observer. This means that if you were to approach a black hole, time for you would pass differently compared to someone far away from it. As you get closer to the event horizon, the boundaries surrounding a black hole, the effects become even more pronounced, and time appears to stretch or dilate significantly. For instance, if an astronaut were to orbit a black hole for what feels like just a few hours, many years could pass for people far away, creating a fascinating but perplexing situation known as gravitational time dilation. This phenomenon is not just theoretical. It has been supported by various experiments, including those involving atomic clocks placed at different altitudes on Earth, which show that time runs slightly faster at higher altitudes where gravity is weaker. When we scale this concept up to the extreme gravity near a black hole, the effects become even more dramatic. The idea of time slowing down near a black hole leads to profound questions about the nature of reality and our understanding of the universe. Imagine a scenario where a spacecraft is sent on a mission to collect data from a black hole. And while the crew experiences only a short amount of time, decades or even centuries could pass for people on Earth. This raises complex questions about aging, communication, and the very fabric of time itself, as the astronauts would return to a world that has changed vastly, while they have aged only a little. Moreover, black holes are not just points of darkness. They can also be incredibly energetic and violent. When matter falls into a black hole, it heats up and emits radiation, creating bright jets of energy that can be seen across vast distances. This process is known as accretion, and it generates intense gravitational forces that can warp space-time, further complicating the relationship between time and gravity. Scientists continue to study these effects using advanced telescopes and theoretical models, as they seek to understand the implications of time dilation not just for black holes, but for the universe as a whole. As we delve deeper into the mysteries of black holes and their impact on time, gravitational waves, those ripples in space and time, are a fascinating aspect of our universe, especially when they originate from the merging of black holes. Imagine two black holes, massive and dense, spiraling around each other, slowly losing energy through the emission of these waves, until, at last, they collide in a spectacular event, releasing an enormous amount of energy, equivalent to the energy output of all the stars in the universe combined, all at once. This phenomenon was first predicted by Albert Einstein in 1916 as part of his general theory of relativity, which describes how massive objects can warp the fabric of space-time. It wasn't until 2015 that scientists at the LIGO Laser Interferometer Gravitational Wave Observatory made history by detecting these waves for the very first time, confirming Einstein's century-old prediction and opening a new window into understanding the cosmos. The detection of gravitational waves is quite remarkable, as it allows scientists to observe events that are otherwise invisible to traditional telescopes. When two black holes merge, they create a disturbance in spacetime, which travels outward at the speed of light. These waves stretch and squeeze the fabric of space itself, which is what LIGO and similar observatories are designed to detect. The instruments use laser beams to measure tiny changes in distance, so when a gravitational wave passes through Earth, it causes minute shifts in the lengths of the arms of the interferometer, changes that are incredibly small, often just a fraction of the diameter of a proton. Each detection provides a wealth of information about the properties of black holes, such as their masses and spins. For instance, the first detection, known as GW 150914, involved two black holes merging to form a single, larger black hole, and it revealed that these black holes were significantly heavier than those typically found in stellar formations. This has led astronomers to ponder the processes that form such massive black holes, as they challenge existing theories about how black holes evolve. Moreover, the study of gravitational waves has the potential to revolutionize our understanding of the universe, as it provides insights into the life cycles of stars, the nature of black holes, and even the very fabric of spacetime itself. Scientists are now able to probe the early universe, gaining a glimpse into events that happened shortly after the Big Bang, and this could help answer fundamental questions about the origins of the universe and its ultimate fate. With ongoing advancements in gravitational wave astronomy, we can expect black holes, those mysterious entities lurking in the depths of the universe, play a surprisingly significant role in cosmic evolution, shaping the very fabric of galaxies and influencing the formation of stars and planetary systems. Formed from the remnants of massive stars that have undergone supernova explosions, these gravitational giants can be categorized into several types, including stellar black holes, which are usually a few times the mass of our Sun, and supermassive black holes, which can contain millions or even billions of solar masses, often found at the centers of galaxies. The presence of supermassive black holes influences the dynamics of the galaxies around them, as their immense gravitational pull can affect the orbits of nearby stars, causing them to move at incredible speeds. This interaction can lead to the formation of new stars, as gas and dust are drawn into the black hole's vicinity, heating up and collapsing under gravity to form new stellar bodies, thus contributing to the ongoing cycle of star formation. Moreover, black holes are not just cosmic vacuum cleaners. They also play a pivotal role in regulating the growth of galaxies. The energy released when matter falls into a black hole can produce powerful jets of particles and radiation, which can blow away gas and dust from surrounding areas. This process can inhibit star formation, essentially controlling how many new stars a galaxy can produce at any given time. As a result, black holes can maintain a delicate balance, ensuring that galaxies do not become overcrowded with stars, which would ultimately alter their structure and evolution. This interplay between black holes and their host galaxies highlights a fascinating aspect of cosmic evolution, where destruction and creation coexist in a complex dance. Additionally, black holes may hold clues to the early universe, as their formation is thought to have occurred shortly after the Big Bang. Some theories suggest that primordial black holes, which could have formed from density fluctuations in the early universe, might have played a role in the distribution of matter and the formation of large-scale structures. Understanding these ancient black holes could offer insights into the evolution of the cosmos, helping scientists piece together the history of our universe from its infancy. The study of black holes also intersects with the field of gravitational waves, as the collision and merging of black holes produce ripples in spacetime that can be detected by observatories like LIGO and Virgo, allowing us to explore the universe in new ways. In the grand tapestry of cosmic evolution, black holes serve as both creators and destroyers, influencing the life cycles of galaxies and the stars within them. Black holes, those mysterious regions in space where gravity is so strong that nothing can escape, have long fascinated scientists and the general public alike. They have been the subject of countless theories and discussions, especially regarding their potential role in the universe's energy dynamics. One intriguing idea is that black holes might be candidates for dark energy, the enigmatic force thought to be responsible for the universe's accelerated expansion. Dark energy makes up about 70% of the universe, yet, despite its significant presence, it remains poorly understood. Some scientists propose that black holes could be linked to dark energy, as their immense gravitational pull might influence the expansion of space around them. The notion that black holes could be tied to dark energy stems from the understanding that black holes are not just simple voids. They are complex objects with unique properties. When a massive star collapses, it creates a black hole, and during this process, it releases a tremendous amount of energy. This energy could potentially contribute to the overall energy balance of the universe, leading some researchers to explore how black holes might interact with dark energy. One theory suggests that as black holes evaporate over time, they could release energy in the form of radiation, which might affect the fabric of space-time and could have implications for dark energy. Moreover, the environment around black holes is extreme, with intense gravitational fields and high-energy phenomena. This environment raises questions about how black holes might create or influence dark, energy-like effects. Some scientists think that the energy released by black holes could produce effects similar to dark energy, leading to repulsive gravitational forces that push galaxies apart, thus contributing to the universe's accelerated expansion. This idea is still under investigation, and while it is a captivating possibility, it is also surrounded by many uncertainties and challenges. Recent research has also examined the possibility that the universe's expansion could be tied to the presence of supermassive black holes at the centers of galaxies. These colossal black holes, which can be millions or even billions of times the mass of our Sun, may play a significant role in shaping the dynamics of their host galaxies and the surrounding space. The relationship between these supermassive black holes and the expansion of the universe is a complex one, ripe for exploration. Some researchers are investigating whether the energy dynamics around these supermassive black holes could somehow interact with, or mimic, the effects of dark energy. Additionally, black holes and dark energy share some fascinating connections in theoretical physics. Some theories propose that the vacuum of space, which includes exotic matter, a term that often sparks curiosity and intrigue, refers to hypothetical materials that possess unusual properties such as negative mass or negative energy density. The idea of exotic matter is particularly fascinating in the context of black holes, which are regions in space where gravity is so intense that nothing, not even light, can escape. The relationship between exotic matter and black holes raises intriguing questions about the nature of the universe and the fundamental laws of physics. One of the most interesting theories related to exotic matter and black holes is the concept of wormholes, which are hypothetical passages through space-time that could connect distant points in the universe. These wormholes, if they exist, would require exotic matter to remain stable, as normal matter would cause them to collapse. This leads to the idea that, if we could somehow create or find exotic matter, it might allow us to explore new dimensions of space and time, possibly even enabling faster-than-light travel. Moreover, black holes themselves may contain exotic matter within their cores, particularly in the form of singularities, where the laws of physics, as we know them, break down. At these points, the density of matter is thought to become infinite, which raises questions about what lies at the center of a black hole. Some theories suggest that the singularity could be surrounded by a shell of exotic matter, influencing the behavior of the black hole and its interactions with the surrounding universe. Additionally, the study of black holes and exotic matter can shed light on the mysteries of dark energy and dark matter, which together make up about 95% of the universe. Dark energy, the force thought to be driving the accelerated expansion of the universe, might have connections to exotic matter, as both involve forces and energies that are not yet fully understood. Researchers are continuously exploring these concepts, using advanced astronomical observations and theoretical physics to unlock the secrets of the cosmos. In essence, the interplay between exotic matter and black holes not only captivates the imagination, but also pushes the boundaries of our understanding of the universe. As scientists delve deeper into these topics, they uncover new insights that could redefine our perception of reality and the fundamental forces that govern it. The quest to understand these phenomena continues, inviting us to ponder the possibilities that lie beyond our current knowledge and inspiring future generations of explorers and thinkers to seek answers to the profound questions that remain. Wormholes, fascinating structures often found in science fiction, have theoretical models that capture the imagination of scientists and enthusiasts alike. These models suggest that wormholes could serve as shortcuts through space and time, connecting distant points in the universe. The concept of a wormhole is rooted in Einstein's theory of general relativity, which describes how mass and energy warp space-time. One of the most discussed models is the Einstein-Rosen bridge, proposed in 1935, which theorizes a connection between two separate points in space-time, although it is believed to be unstable and prone to collapse. Another intriguing model is the traversable wormhole, which was introduced by physicists Kip Thorne and Michael Morris in the 1980s. This model describes a wormhole that could allow for safe passage, theoretically stabilized by exotic matter with negative energy density, a form of matter that has yet to be discovered. The idea of exotic matter raises many questions, as it challenges our understanding of physics. Additionally, there are theories about how wormholes might be created, one being the manipulation of black holes, which are regions of space where gravity is so strong that nothing can escape. Some scientists speculate that if we could find a way to manipulate the gravitational field surrounding a black hole, we might create a stable wormhole. However, these ideas remain speculative, as practical methods for creating or finding wormholes are beyond our current technological capabilities. There are also discussions about the implications of traveling through a wormhole, such as time travel and its paradoxes, which raises questions about causality and the nature of time itself. While these theoretical models offer exciting possibilities, they also highlight the limitations of our current understanding of the universe. Scientists continue to explore the mathematical properties of wormholes, seeking to understand their stability and the conditions required for their existence. Research into quantum gravity and string theory may one day provide insights into the nature of wormholes and their potential reality. As we delve deeper into the mysteries of the universe, the allure of wormholes remains, inviting curiosity and imagination, even as we grapple with the fundamental principles of physics. The journey to uncover the secrets of wormholes is filled with challenges, but it also offers a glimpse into the complexities of space-time, pushing the boundaries of what we know and what we can dream of. The simulation of black hole formation is a fascinating and complex topic that delves into the very fabric of our universe. Scientists, using advanced computer models, have been able to simulate the life cycle of massive stars, which ultimately leads to the creation of black holes. During this process, when a massive star exhausts its nuclear fuel, it can no longer support itself against gravitational collapse. This collapse leads to a supernova explosion, where the outer layers of the star are expelled into space, while the core continues to collapse inward, becoming incredibly dense. In these simulations, researchers study various parameters, including the star's initial mass, rotation, and composition, to see how these factors influence the formation of black holes. For instance, a more massive star tends to produce a black hole with a larger mass, while rotation can affect the black hole's spin and the dynamics of the surrounding environment. The simulations not only help in visualizing the collapse, but also in understanding the gravitational waves that these events produce, which are ripples in space-time that can be detected by observatories like LIGO. Moreover, these simulations provide insights into the processes that might lead to different types of black holes, specifically stellar black holes, which form from the remnants of massive stars, and supermassive black holes, which reside at the centers of galaxies and have masses millions to billions of times that of our Sun. The latter, their formation is still an area of active research, and simulations attempt to uncover whether they form directly from massive gas clouds or grow over time by accumulating matter and merging with other black holes. Recent advancements in simulation technology, such as incorporating more realistic physics and higher resolution models, allow scientists to create detailed representations of black hole formation and to study the subsequent evolution of the black hole and its surrounding accretion disk. An accretion disk is formed by the material that spirals in towards the black hole, heating up and emitting radiation as it accelerates, which can provide valuable information about the black hole's mass and spin. Furthermore, simulations have also been crucial in predicting the behavior of black holes in binary systems, where two black holes orbit each other and can eventually merge, producing gravitational waves detectable by advanced instruments. These simulations help scientists to better understand the frequency of such events and their implications for our understanding of the universe. Black holes, once purely theoretical constructs, are now at the forefront of astrophysical research, and the simulations of their formation continue to push the boundaries of our knowledge. Black holes, those mysterious regions of space where gravity is so strong that nothing can escape, have captured the imagination of people for decades, appearing not only in scientific discussions, but also in various forms of popular culture. From movies to music, and books to television shows, black holes have become a fascinating subject, often used as a metaphor or a plot device, drawing audiences into their enigmatic allure. Movies like Interstellar have portrayed black holes with remarkable visual effects, showcasing the concept of time dilation, where time moves differently at the edge of a black hole compared to the outside world, a notion that deeply resonates with audiences and sparks curiosity about the nature of time and space. The depiction of black holes in these films is often grounded in real scientific theories, which adds a layer of intrigue, as viewers come to realize that these fantastical elements are rooted in actual physics. In literature, black holes have served as a powerful metaphor for the unknown, representing everything from existential dread to personal struggles. Clarke and Isaac Asimov have woven black holes into their narratives, exploring themes of human curiosity and the limits of knowledge. In graphic novels and comic books, Black holes often serve as gateways to other dimensions, allowing characters to journey through space and time, which captivates readers and fans of all ages. This blend of science and imagination encourages people to think about the universe in new ways, making complex ideas more accessible and engaging. Television shows, too, have embraced the concept of black holes, using them to create suspenseful storylines and provoke thought. Series like The Big Bang Theory and Doctor Who have featured black holes in humorous or dramatic contexts, prompting viewers to ponder the implications of such cosmic phenomena while being entertained. The casual yet informed discussions about black holes in these shows can inspire audiences to delve deeper into astrophysics, encouraging a fascination with the cosmos that extends beyond the screen. Even in music, black holes have inspired songs and lyrics, often serving as symbols of longing, loss, or the vastness of existence, appealing to our emotions and inviting us to reflect on our place in the universe. The portrayal of black holes in popular culture not only entertains, but also educates, sparking interest in astronomy and science. By blending fact with fiction, these representations make the complex concepts surrounding black holes more relatable, allowing people to engage with ideas that might otherwise feel too abstract or challenging. As we continue to explore the universe, the intersection of science, black holes, those mysterious and fascinating objects in our universe, have captivated scientists and the general public alike for decades. As we look toward the future of black hole research, we find ourselves at a thrilling crossroads of science and technology. The advancements in telescopes, like the Event Horizon Telescope, have already allowed us to capture the first image of a black hole's event horizon, an achievement that was unimaginable just a few years ago. With ongoing developments in observational technologies, we can expect even more detailed images and data about black holes, which will help us understand their formation, growth, and the role they play in the cosmos. One exciting area of future research involves the study of gravitational waves, which are ripples in space-time caused by massive objects, such as colliding black holes. The Laser Interferometer Gravitational Wave Observatory, or LIGO, has already detected several events, and, as technology improves, we will likely observe more collisions and mergers, providing insights into how black holes interact with each other and how they evolve over time. This will not only deepen our understanding of black holes, but also of the fundamental nature of gravity itself, potentially leading to new theories that bridge general relativity and quantum mechanics. Moreover, there is a growing interest in studying supermassive black holes, which reside at the centers of galaxies, including our own Milky Way. These giants are crucial to understanding galaxy formation and evolution. Future missions, such as the James Webb Space Telescope, will allow astronomers to peer deeper into the cosmos, observing the environments surrounding supermassive black holes and uncovering the mysteries of their influence on galactic dynamics. By examining the gas and stars that orbit these massive entities, researchers hope to learn more about how black holes grow and how they may have shaped the structure of the universe. Additionally, theoretical physicists continue to explore the enigmatic nature of black holes through advanced mathematical models and simulations. Concepts like Hawking radiation, proposed by Stephen Hawking, suggest that black holes can emit radiation and eventually evaporate over time. Future research may provide experimental evidence for such phenomena, potentially leading to breakthroughs in our understanding of the life cycle of black holes. As we delve into the future of black hole research, we can also anticipate interdisciplinary collaborations. Astrophysics, quantum physics, and even computer science will converge as researchers use complex algorithms and machine learning to analyze vast amounts of data generated by telescopes and gravitational wave detectors. This collaboration will enhance our ability to identify patterns. Black holes are some of the most mysterious and fascinating objects in the universe, capturing the imagination of scientists and space enthusiasts alike. They are formed when massive stars exhaust their nuclear fuel and undergo a gravitational collapse, leading to an incredibly dense point called a singularity, surrounded by an event horizon, which is the point of no return. Once anything crosses this boundary, it cannot escape the intense gravitational pull of the black hole. In the life cycle of a star, this transformation occurs after the star has spent millions or even billions of years fusing hydrogen into helium and then progressing through heavier elements, like carbon and iron, during its later stages. When a massive star runs out of fuel, it can no longer support itself against gravitational forces, leading to a spectacular explosion known as a supernova, which blasts away the outer layers of the star, leaving behind the core. If this core is more than about 3 times the mass of the Sun, it will collapse into a black hole. Interestingly, black holes play a crucial role in the evolution of galaxies. They are often found at the centers of galaxies, including our own Milky Way, where they exert a powerful influence on the surrounding stars and gas. The gravitational pull of a supermassive black hole can impact the motion of stars within the galaxy, leading to the formation of new stars and influencing the overall structure of the galaxy. Some scientists believe that the growth of black holes is linked to the growth of galaxies themselves, suggesting a deep connection between these two cosmic phenomena. Additionally, the intense gravitational fields near black holes can lead to the creation of jets, which are streams of particles that are ejected at nearly the speed of light. These jets can have a significant effect on their surroundings, impacting star formation in nearby regions. Moreover, black holes are not just destructive entities. They also contribute to the recycling of matter in the universe. When stars orbit close to a black hole, they can lose material, which can be pulled toward the black hole and heated to extreme temperatures as it spirals in, forming an accretion disk. This process emits vast amounts of energy, often in the form of X-rays, allowing astronomers to detect black holes indirectly. This energy release can influence star formation in the galactic environment, showing that black holes participate in a complex and dynamic ecosystem. As for the fate of stars in relation to black holes, it's important to understand that not all stars end up as black holes. Stars with lower masses, like interstellar travel, a concept that fascinates many, is the idea of traveling between stars, often invoking thoughts of advanced technology and the mysteries of the universe. One of the most intriguing aspects of this journey is the role of black holes. Black holes, formed from the remnants of massive stars that have undergone gravitational collapse, possess gravitational fields so strong that nothing, not even light, can escape them. This incredible force can warp space and time, creating fascinating implications for travel across vast distances. The theory of general relativity, proposed by Albert Einstein, suggests that black holes could allow for shortcuts through the universe, known as wormholes. These hypothetical passages could connect distant points in space-time, potentially enabling interstellar travel in a way that seems straight out of science fiction, yet remains within the realm of scientific possibility. However, the journey near a black hole would not be without its challenges. The immense gravitational pull creates what is known as the event horizon, a point of no return. Once an object crosses this threshold, escape is impossible. Moreover, the intense radiation emitted by matter as it spirals into a black hole can be deadly, making it crucial for future explorers to develop technologies that can withstand such extreme environments. Scientists and engineers are continuously exploring theories on how we might harness the properties of black holes, such as using the energy emitted from them for propulsion or utilizing their gravitational influence to slingshot spacecraft to greater speeds. The idea of using black holes for travel also raises questions about the nature of time. According to relativity, time moves slower in strong gravitational fields, meaning that astronauts traveling near a black hole could experience time differently than those remaining on Earth. This phenomenon, often referred to as gravitational time dilation, adds another layer of complexity to the concept of interstellar travel, as it could result in significant differences in the passage of time for travelers versus those who stayed behind. While the concept of interstellar travel and black holes is still theoretical, ongoing research in astrophysics continues to uncover new insights. Telescopes, like the Event Horizon Telescope, have captured images of black holes, providing a clearer understanding of their structure and behavior. These advancements give scientists hope that one day, humanity may not only explore our own solar system, but also venture into the depths of interstellar space, uncovering the secrets that lie beyond our planet. The journey into the cosmos may one day reveal the interconnectedness of galaxies, as well as the potential for life beyond Earth. Igniting the black holes, fascinating and mysterious entities in the universe, challenge our understanding of space, time, and even the concept of infinity. A black hole forms when a massive star exhausts its nuclear fuel, collapsing under its own gravity, creating a region in space where the gravitational pull is so strong that not even light can escape it. This is why they are called black holes, as they are invisible against the backdrop of space. The boundary surrounding a black hole is called the event horizon, and once something crosses this threshold, it cannot return. The idea of infinity comes into play when we consider what happens at the center of a black hole, known as the singularity. Here, the laws of physics as we know them break down, and gravitational forces become infinitely strong, leading to a point of infinite density. This poses intriguing questions about the nature of the universe, as it suggests that our current understanding of space and time may not apply in the same way within a black hole. Moreover, black holes are not just cosmic vacuum cleaners, they play a crucial role in the evolution of galaxies. Supermassive black holes, found at the centers of most galaxies, can influence star formation and the movement of stars around them. Observations have shown that the mass of a supermassive black hole is often related to the mass of the galaxy it resides in, suggesting a connection that scientists are still working to fully understand. In addition, black holes are not solitary. They can exist in pairs or even larger clusters. When two black holes orbit each other, they can eventually merge, releasing immense amounts of energy in the form of gravitational waves. These ripples in spacetime were first detected by the LIGO Observatory in 2015, confirming a prediction made by Albert Einstein a century earlier. The study of these phenomena opens up new avenues in understanding the structure of the universe and raises questions about the nature of infinity itself as we ponder what lies beyond the event horizon and the mysteries that may lurk in the depths of these cosmic giants. As we explore black holes, scientists are also investigating the possibility of wormholes, which are hypothetical passages through spacetime that could connect distant points in the universe. While purely theoretical at this point, if they do exist, wormholes could provide a way to travel vast distances in the blink of an eye, further blurring the lines between time, space, and infinity. This interplay between black holes, the concept of infinity, and the detecting black holes, those mysterious regions in space where gravity pulls so strongly that not even light can escape, requires a variety of observational techniques, each offering unique insights into these enigmatic objects. One of the primary methods used to detect black holes is through the observation of the effects they have on nearby stars and gas clouds. For instance, when a black hole is part of a binary system, it can exert a powerful gravitational pull on its companion star, causing it to orbit around the black hole in a predictable manner. By measuring the speed and path of this orbiting star, astronomers can calculate the mass of the black hole, even if it remains invisible to telescopes. This technique, known as dynamical mass estimation, relies heavily on precise measurements of the star's motion, which can be achieved using advanced telescopes equipped with spectrometers. Another fascinating technique involves the detection of X-rays emitted by hot gas as it spirals into a black hole, a process known as accretion. As matter falls toward the black hole, it forms an accretion disk, heating up to extreme temperatures and emitting X-rays in the process. Observatories such as the Chandra X-ray Observatory or the European Space Agency's XMM Newton are specifically designed to detect these high-energy emissions, allowing scientists to identify potential black holes based on their X-ray signatures. This method has led to the discovery of many stellar black holes, which are formed from the remnants of massive stars that have exploded in supernova events. Gravitational waves, ripples in space-time caused by the acceleration of massive objects, have also revolutionized our understanding of black holes. The detection of gravitational waves from colliding black holes, first observed by the LIGO Observatory in 2015, provides a completely new way to observe these cosmic giants. When two black holes merge, they produce gravitational waves that can be detected on Earth, offering direct evidence of their existence and properties. This technique not only confirms the presence of black holes, but also allows scientists to study their masses and spins, enriching our understanding of their formation and evolution in the universe. Moreover, the study of gravitational lensing, where the gravitational field of a black hole bends the light from objects behind it, can reveal their presence. When light from distant stars passes near a black hole, it can be distorted and magnified, creating multiple images or rings around the black hole. By analyzing these effects, astronomers can infer the mass and location of the black holes, those mysterious regions of space where gravity is so strong that nothing, not even light, can escape, have fascinated scientists and the public alike for decades. They form from the remnants of massive stars after they exhaust their nuclear fuel, collapsing under their own gravity. But the story of black holes becomes even more intriguing when we delve into the realm of quantum gravity, a field that seeks to unite the principles of quantum mechanics, which governs the behavior of tiny particles, with general relativity, Einstein's theory of gravity that describes the large-scale structure of the universe. One of the most pressing questions in modern physics is how these two theories can coexist, especially in the extreme conditions near a black hole. As we approach a black hole, things get very strange. The event horizon, the point of no return, marks the boundary where the gravitational pull becomes so intense that escape is impossible. The behavior of matter and energy in this region is not yet fully understood, and this is where quantum gravity comes into play. One of the key ideas in quantum gravity is that space and time are not fixed backgrounds, but rather, they can be influenced by the objects within them. This concept challenges our traditional views of black holes, suggesting that they might not be as simple as we once thought. Interestingly, researchers have proposed that black holes could be connected to the fabric of the universe in ways we don't yet understand. For example, some theories posit that information, which seems to be lost when something falls into a black hole, is actually preserved in a way that we cannot yet comprehend. This idea, known as the information paradox, raises profound questions about the nature of reality and our understanding of the universe. Moreover, scientists are investigating whether black holes might serve as portals to other regions of space or even to other universes, a concept that stretches our imagination to its limits. In recent years, advancements in technology have allowed us to observe black holes more closely than ever before. The Event Horizon Telescope, a global network of radio telescopes, captured the first ever image of a black hole in 2019, providing visual evidence of their existence and giving us new insights into their properties. This groundbreaking achievement has opened up new avenues for research, as scientists continue to explore how black holes interact with their surroundings and how they might fit into the larger fabric of quantum gravity. The study of black holes and quantum gravity is not just an academic pursuit. It has real implications for our understanding of the universe and our place. The exploration of black holes, those enigmatic cosmic entities, raises intriguing ethical implications that deserve careful consideration. As scientists delve deeper into understanding the nature of black holes, the potential consequences of their research extend beyond the realm of physics and astronomy. One significant ethical concern is the impact of black hole research on our understanding of the universe and our place within it. As we learn more about these massive gravitational wells, the possibility of discovering advanced civilizations or even the fate of our own existence in relation to the cosmos becomes a profound question. The idea that black holes could be gateways to other dimensions or universes invites not only scientific inquiry, but also philosophical reflection on the nature of life and intelligence. Moreover, The technological advancements that come from black hole research present their own ethical dilemmas. For instance, the sophisticated instruments used to study these phenomena, such as gravitational wave detectors, require substantial funding and resources. This raises questions about the allocation of public funds and whether the investment in such research is justified, especially when there are pressing issues on Earth that require attention, like climate change or poverty. The debate over where to direct scientific funding is an ongoing ethical conversation, as scientists must balance the pursuit of knowledge about the universe with the immediate needs of humanity. Additionally, there is the issue of the potential misuse of knowledge gained from black hole research. Understanding the mechanics of black holes could lead to advances in energy production, potentially harnessing power from the immense gravitational forces, but it could also open doors to dangerous technologies if exploited for harmful purposes. The ethical responsibility of researchers, therefore, extends to considering how their discoveries could be used and ensuring that the knowledge serves the greater good rather than creating new forms of harm. The cultural implications are also significant. The way black holes are portrayed in popular media, from movies to documentaries, influences public perception and understanding of these cosmic phenomena. This can lead to misconceptions or fear, shaping how society views scientific exploration and the unknown. Scientists must navigate the responsibility of communicating their findings accurately, fostering public interest while avoiding sensationalism that could distort the realities of black hole physics. Moreover, there is the ethical responsibility of inclusivity in black hole research. As this field progresses, it is crucial to ensure that diverse voices are heard in the scientific community. Engaging individuals from different backgrounds and cultures can enrich the dialogue around black holes, bringing various perspectives on the implications of such research. This inclusivity can help humanity address the ethical questions that arise from our quest to understand these mysterious objects, ensuring that, exploring black holes, those mysterious regions of space where gravity is so strong that nothing, not even light, can escape, has long captured the imagination of scientists and the public alike. As our understanding of the universe evolves, so too do the technologies that enable us to study these enigmatic objects. One of the most promising future technologies is the development of advanced gravitational wave detectors. Gravitational waves, ripples in space-time caused by massive objects like merging black holes, can provide invaluable information about these phenomena. The next generation of detectors, such as the planned space-based LISA, or Laser Interferometer Space Antenna, aims to be much more sensitive than current ground-based observatories, allowing us to detect events from much farther away, which could lead to groundbreaking discoveries about the nature of black holes. In addition to gravitational wave detection, the use of powerful telescopes is set to revolutionize our understanding of black holes. The Event Horizon Telescope, which produced the first-ever image of a black hole's event horizon, is just the beginning. Future telescopes, equipped with even higher resolution and more advanced imaging techniques, may allow us to observe the dynamics around black holes in unprecedented detail. This could help answer fundamental questions about how black holes grow, how they influence their surroundings, and how they might be connected to the formation of galaxies. Moreover, advancements in computer simulations and artificial intelligence are expected to play a crucial role in black hole research. Simulations can model the extreme conditions near a black hole, allowing scientists to predict how matter behaves in such environments. By harnessing the power of AI, researchers can analyze vast amounts of data from various sources, like telescopes and gravitational wave detectors, identifying patterns and anomalies that may lead to new insights about black holes. This synergy between advanced simulations and AI could enable a deeper understanding of the intricate processes at play in these cosmic giants. Another exciting avenue for future exploration involves the concept of black hole imaging. Scientists are working on technologies that could allow us to capture more detailed images of black holes, including the surrounding accretion disks and jets of particles that are often ejected at incredible speeds. By studying these features, researchers hope to gain insights into the physics of black holes, including the mechanisms of energy and mass transfer in their vicinity. Space missions specifically designed to study black holes are also on the horizon. Concepts like an orbiting observatory that can observe high-energy X-rays emitted by black holes could provide a wealth of information. These missions would